Hi everyone, my name is Zhen Zhigong. I am a PhD student from Harvard University. Today I'd like to introduce our project, Microscope, which is the first diagnostic tool that can zoom into microsecond level events in network functions. This is a joint work between Harvard University and AT&T. Nowadays, network function virtualization, NFV, is becoming popular. We see a lot of virtual network functions in industry. For example, there are network translators, load balancers, firewalls, and VPNs. They could be developed by different vendors. An ISP like AT&T could collect those network functions, deploy them in the ISP network, and run them in a DAG topology. Finally, it could start to process user traffic. As network function transform from hardware to software, NFV brings many benefits such as flexible deployment, easier development, and cheaper price. But such benefits only come with good performance, which is critical in the success of NFV because NFs runs in software. Unfortunately, those performance requirements are hardly achieved in real deployment of NFV. In reality, we see a lot of problems in NFV, including high tail latency, low throughput, and packet jobs. In addition, usually the length of the NFV topology could be as long as 6 to 7 network functions. Even if only one network function has problem, could affect the whole NF chain. Furthermore, current NFV chains appear in different ISP networks, data center networks, as well as cellular networks. And thus, almost every user traffic will be processed by an NFV chain. As a result, NFV performance diagnosis is critical in the success of NFV. Our survey with 19 network operators shows that many operators spend more than 12 hours on 10 to 100 NFV performance problems per month. However, diagnosing performance problems is not straightforward and causes many blame games. Here is an example of an NFV chain. After seeing a long tail latency problem in the VPN, the operator first suspects that the VPN vendor is the culprit because there could be a bug in the VPN. But after further diagnosis, there is no problem found when running the VPN alone. Then the operator starts to suspect that user traffic is the culprit because it could send traffic bursts. But this is not the case this time. Finally, the operator finds that the problem is located in the firewall because there is a misconfiguration in the firewall. In reality, things could be much more complex. When problem happens, there are always such blame games among different parties, including different network function vendors, different operators, and the user traffic. Therefore, when problems happen in NFV, our goal is to identify the correct causal relations between the correct culprit and the performance problem. And this is a harder task than diagnosis in distributed systems. Traditional distributed systems focus on request latencies, which is usually millisecond level. But in NFV, we focus on packet latencies, which is usually in microsecond level. The requirement is much tighter. So many microsecond level events start to become impactful in NFV systems, such as CPU interrupts, cache misses, or traffic bursts. These microsecond level events make prior solutions ineffective in NFV. Prior solutions use time-based correlations. They assume that events happening in the same time window with the problem are root causes. But this assumption becomes invalid in NFV because of so many micro-level noises. Let's use the previous example to show this. Here we show a timeline of different events in the above example. In the beginning, a misconfiguration in firewall is triggered at this time, so the queue in firewall starts to build up. After the queue was built up, the VPN starts to suffer from long-tail latency during this time period. In the meanwhile, there was also some irrelevant microsecond level noisy events. As we can see, the misconfiguration and the latency problem happen at disjoint time periods. In this situation, it's really hard to define a fixed time window size. If the time window size is too small, we can miss such causal relation between the misconfiguration and the long latency. If the time window is too long, the time window could include a lot of different noisy events, which makes it harder to identify the correct causal relation. This experiment showed why diagnosis in NFV is uniquely challenging because of the micro-level events. In concrete, there are two types of challenges. The first challenge is that impact can propagate over time. In the example, the direct cause of the long latency is there is a burst arriving to the VPN. Now we show the timeline of the traffic rate and latency in the VPN. In the beginning, there's only a low rate of background traffic and the latency keeps at a low number. However, then the burst arrives during this time, which raises up the latency as well. After the burst ends, the traffic rate keeps at a normal level, but the long latency keeps for a while after the burst. We found that the burst happens during this time, while the long latency happens during this time, which is much longer than the burst. The reason for this lasting impact of burst is shown in the right figure. As we can see, the queue length in VPN starts to grow when the burst arrives and still keeps at a high level after the burst, because packets in the queue need to take some time to be processed. As a result, the impact in NFV could propagate over time. The second challenge is that impact can propagate across network functions. Specifically, in the same example, now let's move our focus to the firewall. Why the firewall sends the burst? Here are the timeline of input rate and output rate of firewall. In the beginning, the input rate is normal and the output rate is equal to the input rate. At this time, an incident misconfiguration is triggered by certain flows, which causes the throughput of firewall to a low number. Therefore, even if the input rate keeps the same, the output rate is very small. After the configuration ends, the output rate becomes much higher than a normal value, which sends a burst to the VPN. The reason for the burst is during the misconfiguration time, the queue is built up with many packets, and after the misconfiguration ends, the firewall sends those packets as fast as possible, which forms a burst. As a result, the misconfiguration in firewall propagates to the VPN, which means the impact can propagate across network functions. In summary, we found that the impact of problems could propagate over time and across different network functions. Besides, another challenge is the large amount of root causes and victim packets, which is hard for operators to focus. The key insight of our system Microscope is that the queue can reveal all the propagations. In the above example, by tracing back packets in the queue of VPN, we can learn when the traffic burst arrives and affects VPN, even if the impact propagates over time. Also, by tracing back packets in the queue of firewall, we can learn when the firewall buffer packets in the queue and when the firewall sends the burst. Therefore, we can learn the impact propagation even if it is across different network functions. Here is the architecture of Microscope. In the runtime, Microscope collects queuing data from the NFV, which could be used to identify victim packets NFs and perform diagnosis. After collecting the data and the victims, Microscope then performs offline diagnosis for those victims. The diagnosis consists of 3 steps, including local diagnosis, propagation diagnosis, and the pattern aggregation. I will introduce them now. Here is a roadmap for how Microscope resolves the challenges. We first show Microscope uses local diagnosis based on queuing period to resolve the first challenge. The first step in Microscope local diagnosis performs diagnosis based on queuing period. So what is queuing period? Let's assume that a packet P is suffering from a long tail latency problem at NFF. Because there is a long queue in the NFF, we claim that the formation for the long queue is not only due to the current packets in the queue, but also all the history packets starting from the time when the queue just starts to buffer packets, which is at this time point in this figure. Therefore, we define the queuing period in this way. It starts at the time when the queue starts to buffer packets and ends at the time when the victim packet P arrives. So what can we get from the queuing period? Let me show you now. When we see a victim packet having a long latency problem at NFM, the target of local diagnosis is to identify whether the problem is local or located in upstream network functions. Microscope achieves it by checking the input rate and the processing rate during the queuing period. If the input rate is higher than the traffic capacity of NFF, we then conclude that the problem is located in the upstream. If the processing rate of F is lower than expected, then we can conclude that the problem is local. Note that the rate is computed during the whole queuing period, and thus we can detect the cause, even if it does not exist at the current time. Now let's look at the second challenge. Microscope runs propagation diagnosis based on time span analysis to resolve this challenge. After the first step, if the problem is located in the upstream, we need further diagnosis to find out which upstream network function is the culprit. This step is used to do it. In the first step, we know that the upstream network functions are sending traffic bursts to the victim network function. So in this step, the key question is which upstream network function makes the traffic bursty. Microscope uses a method named time span analysis to achieve it. Let's look at these steps. The following three lines represent the timeline of packet arrival in NF A, B, and F. Assume that packets in the queuing period arrive at F during this time. We then trace back those packets in upstream network functions and find out that those packets arrive at B during this time period and arrive at A during this time period. As a result, we can find that after the processing of B, the time span of packets becomes shorter, which means that packets become more bursty after B. Therefore, network function B is the culprit. Moreover, based on how shorter the time becomes, we can quantify the impact of NFB. Using time span analysis, Microscope can detect cause even if it is located in different network functions. The diagnosis algorithm has several challenges. The first challenge is, what if the time span becomes larger after NF during time span analysis? As shown in the figure, NFB makes the time span larger, so the time span in C is similar as that in A, even if A makes the traffic bursty. Microscope handles this situation as follows. First, NFB is definitely not the culprit. Furthermore, because B makes the time span larger, so it mitigates or hides the impacts from A. In this situation, A is not the culprit as well because of the help of B. Second challenge, how to perform time span analysis on a DAG topology. Previously, we only introduced time span analysis on a single chain. Things become more complex when the topology is a DAG, because during the queuing period, different packets may come from different paths. Microscope will perform time span analysis on each path, and the definition of time span on each network function is adjusted to make it reasonable. Please refer to our paper for more information. Here is the third challenge. Assume that in time span analysis, we find that B makes the traffic bursty, and we know that B is the culprit. However, the diagnosis does not end here because we still need to understand why B makes the traffic bursty. Microscope needs to perform recursive diagnosis on NFB to understand it, which means that we treat B as a victim and perform local diagnosis on B recursively. Now let's look at the third challenge. Microscope runs pattern aggregation to generate a brief diagnosis report. After finding out all the causal relations between the culprit and the victim, we find out that there could be a very long list of causal relations. Therefore, the next step of Microscope is to aggregate them into a brief report. Microscope leverages autofocus algorithm, which is an algorithm to find the hierarchical heavy hitters in a traffic, to aggregate those causal relations into causal relation patterns. There is a challenge in using autofocus here. Autofocus is usually to aggregate traffic where we mainly focus on 5 tuple. However, here, each causal relation has as many as 12 fields, which makes the speed of autofocus much slower. To address this challenge, Microscope uses an approximation method. You can check our paper for more details of this approximation. Now let's look at our evaluation. We run an example NF DAG as shown in the figure, which is referred in E2 paper in SOSP 15. Each NF runs on 1 VM using DPDK. We serve KIDA 16 traffic to our NF DAG. For the problems to be diagnosed, we inject 3 kinds of problems, including traffic bursts, interrupts, and firewall misconfigurations. We compare our microscope with netmatic system, which is a typical diagnosis system using time-based correlation. We configure netmatic with the best time window setting. The output of each system is a ranked list of root causes for each victim packet, and we compare the accuracy of the 2 systems using this output. Overall, Microscope has much higher accuracy than netmatic. This figure shows the result. The x-axis represents the cumulative percentage of victim packets, and the y-axis represents the rank of the correct cause for each victim packet. Let's look at certain points. This point means for 89.7% victim packets, Microscope successfully ranks the correct cause first, while for only 36% victim packets, netmatic ranks the correct cause first. We checked the results from netmatic and observed that netmatic failed to find causal relations with a fixed time window, because it usually misses correlation with many noisy events exist in the same time window. We also run Microscope without injecting problems to show how it works in natural environments. We served the NF DAG with 80% load. Here are our observations. There are 21.7% of all victim packets are caused by propagation, and 10.9% of them are caused by at least 2 hop propagation. This means that impact propagation are common in real NF deployment, and Microscope is a great tool to detect them. We show some other evaluation results here. We changed our evaluation setting and found out that Microscope outperforms netmatic in different burst sizes, in different interrupt intervals, and in different levels of impact propagation. Microscope also performs good in pattern aggregation. One evaluation shows that Microscope successfully converts 84K causal relations into 80 patterns. Here is the conclusion. We observed that NF3 performance is critical to the success of NFV, which means NF3 diagnosis is very important. However, we found out that there are key challenges in diagnosing NF3, which is the impact of problems could propagate over time and across different network functions. We propose Microscope, which leverage queuing period and time span analysis to understand such impact propagation. It also uses autofocus to provide a brief diagnosis report. Our evaluation results show that Microscope achieves much higher accuracy than existing solutions. Microscope is the first tool focusing on microsecond level performance problems. We expect that Microscope should be generically useful to other large-scale systems as we get higher speed and lower latency. Thank you very much.